Parametric equations. Using trig identities to convert parametric equations to their Cartesian form. Example 1. So we have two parametric equations. The parameter is t. I've rearranged the equation for x to make sine t the subject, and I've rearranged the equation for y to make cos t the subject. Now sine squared plus cos squared is equal to 1, a standard identity, and we have sine t is x minus 2. This is sine squared, so if you square both sides we put x minus 2 in brackets and square, and likewise we've got cos squared t, so to square both sides we put y plus 3 in brackets and we square, like so. You might recognize this as the equation of a circle where the center is at 2 minus 3. This is r squared, so the radius is equal to 1. Example 2. A, B and r are constants. T is the parameter. So I've rearranged this equation to make cos t the subject, and I've rearranged this equation to make sine t the subject. Sine squared plus cos squared is equal to 1, so I need to square both sides here and here and then substitute into our identity like this. The power goes on the numerator and denominator again, so we have this, then multiplying by r squared throughout. So I've just rearranged these terms, and what we have here is the equation of a circle which is centered on the point with coordinates a, b and with radius r, and in here a, b and r are constants because the center of the circle is fixed at a particular point and the radius is fixed. A point that's moving around the circumference of the circle will have an x and y coordinate that's varying. So x and y are the variables, a, b and r are constants. So we have the equation of a circle given in parametric form or Cartesian form, where a and b are the coordinates for the center and r is the radius. So a, b and r are constants. Example 3. So we have parametric equations. T is the parameter, and t can be any value between minus pi over 2 to pi over 2. So method 1, the first thing we see is that we have a double angle here, sine 2t. So we can write that as 2 sine t cos t. Now the sine t here we can replace with x from this equation. So y is equal to 2x cos t. We still have this parameter t here in this term. We still need to eliminate this. So I'm going to start with this equation, x equals sine t, and square both sides, and sine squared is equal to 1 minus cos squared. Rearrange to make cos squared t the subject. Square root both sides, you get a plus or minus because we have an even power. Now I'm going to use the cast diagram to determine whether it's the positive or negative solution. So t is an angle between minus pi over 2, so if that's 0, then on the cast diagram here, then minus pi over 2 is here. So negative angles going clockwise, positive angles going anti-clockwise, so this is pi over 2. An angle in this interval means it's in quadrant 1, 2, 3 or quadrant 4, and we can see that in quadrants 1 and 4 cosine always has a positive ratio. So that's cos of an angle is equal to the cosine ratio, and it has to be positive according to this diagram, so we need the positive solution, like so, which we then substitute into here, and we have the Cartesian form. Now method 2 starts off the same as method 1 up to here, but how we deal with the cos t term differs. So I'm starting off with sine t is equal to x here. Now sine is opposite over the hypotenuse, so x over 1. If we represent this information in a right angle triangle and then work out the missing side, and our angle t is here, so this is using Pythagoras' theorem, then what we're looking for, which was cos t, the cosine of t is the adjacent over the hypotenuse. Now whenever we do the right angle triangle method, we get the ratio from the triangle, but we never get the sign of the ratio, whether it's positive or negative. So just like in the previous part, here we still need to verify if our ratio is positive or negative. So cos t is equal to root 1 minus x squared, this the adjacent, over the hypotenuse over 1, which simplifies to this. Cast diagram, same as before, and we know that in this interval, for our angle, the cosine ratio will be positive, because we're either in quadrants 1 or 4, where cosine has a positive ratio. So checking the sign, I know that this will be positive. So finishing off, we have 2x cos t, and cos t is root 1 minus x squared. We substitute that in, and we now have our Cartesian equation. We still need to look at domain and range. We'll start with domain. So the domain comes from x is equal to, from the parametric equations. So I've done a sketch of sine t. So t is an angle, it goes on the horizontal axis, and x is the sine ratio, it goes on the vertical axis. It may seem a bit unusual to have x on the vertical axis, but this is exactly the way it is. Now t can take any value in this interval, so from minus pi over 2 to pi over 2, and in this interval we can see that the values of x can go from minus 1 to plus 1. So our x, or domain, is this. Moving on to the range, so y equals sine 2t has this graph. So it differs from the previous graph that was for sine t, because we have a double angle here, and there's a transformation applied to that graph to get this one. It's a times a half stretch in the horizontal direction. So we can see that y, which is on our vertical axis, has any value between minus 1 and plus 1. So our range, which is given in terms of y, is this. Question 3 part B, we have the same parametric equations as before, but the conditions for t have changed. Now t can be any real number, so it could be a positive or a negative angle. So as before, we've got sine t replaced with x, nothing different there. And then I've used the right angle triangle method, so sine t is equal to x. We work out the missing side using Pythagoras' theorem, and then cos t will be the adjacent over the hypotenuse. But remember, the right angle triangle method only gives you the ratio. You still have to check whether it's a positive or a negative sign with the cast diagram. Now the condition for the angle this time is that it could be pretty much anything, positive or negative. So our angle could be anywhere on the cast diagram, which means we could have positive ratios in quadrants 1 and 4, we can have negative ratios in quadrants 2 and 3. There's actually 2 equations in here, like this. So y equals 2x root 1 minus x squared, and y equals minus 2x root 1 minus x squared. Now these are the parametric equations with their graph, and the graph of y equals 2x root 1 minus x squared looks like this, and they're not the same. There's some similarity there. You've got half the graph, half is missing. And the graph of y equals minus 2x root 1 minus x squared, that's the other half of the graph. And now I'm going to superimpose these. I'm going to put them together like this, and you can see that both graphs combined give the original parametric graph. And you can also see the domain was between -1 and +1, so x is greater than or equal to -1, less than or equal to 1, and the range was greater than or equal to -1 but less than or equal to 1.